Okay, well, we can get started. Do people have any questions that they'd like to go over? Any questions? No? Okay. Well, we can talk about maybe some orthogonality. Even though it doesn't feel like it, spring break is starting tomorrow. So maybe we can take this one, we can make this section a little short. We can talk about orthogonality, a new topic. A pretty important topic, actually. Orthogonality, we're going to see for a while, for the next, month or so. And it's pretty important to kind of understand a little more about the geometry of vectors, which is kind of what Nikhil talked about in lecture. Right, so you've seen some stuff like this before. You've seen like dot products before. So just as a warm up, maybe. Or maybe if you haven't seen dot products, it's not too hard to compute a dot product. Let's compute the dot product of some things. Let's compute A dot B, where A and B are just some vectors. 1, 2, 0, 4. B, -1, 0, 3, -2. Right. So the dot product, hopefully this is just quick warm up, quick review for everyone, is you sum over entry-wise products. So you have 1 times -1 plus 2 times 0 plus 0 times 3 plus 4 times -2, right? And these are just coming from each of these entries and so forth. And you get some number. You get -1 minus 8, -9. Yep. And so another way to write this, just to recap again, the dot product of two vectors is also written in matrix notation as A transpose B, right? A transpose here is a 1 by n matrix. This is an n by 1 matrix. So the result is a 1 by 1 matrix, which you just identify with a real number. Right? 1, 2, 0, 4. Remember, the transpose flips all rows and columns. And so you get negative. Okay, so that was just kind of a warm up. So we're all on the same page on dot product. So the dot product takes in two vectors and outputs a real number. Dot product takes in two vectors and outputs a real number. And we're going to generalize this later in the course to arbitrary vector spaces. But for now, we'll just stick with dot product. And kind of the meaning of the dot product, this has kind of gone over a little in section, is that dot products give you a notion of angle. And in turn, a notion of distance. Right? And this is going to be very important for us because, we can't really visualize vectors in Rn for n greater than 3, but we can still define what it means, what the angle between two vectors is, and we can still define what it means to be close to another vector. So like later on, we'll deal maybe with arbitrary vector spaces where you might want to say something like, what is the closest polynomial to some space of polynomials. And to answer this question, you need some notion of distance. So that's what the dot product gives us. So we'll answer this later in the course. This is later. For now, we'll stick with column vectors. Right, and the way it defines angle for us is that we have this proposition, which we're not going to use that much in this class, but it's just nice to know. So if U and V are in Rn, then U dot product V is the norm of U, norm of V times cosine of this angle between them, where theta is, so if you have U, V, and this is theta. Right, so for vectors in R2 or in R3, theta is like a concrete thing. You kind of know, you can visualize what theta is. But for U and V, just for an arbitrary Rn, where n is greater than 3, this is kind of a definition of what the angle between two vectors is. We can just define the angle between two vectors to be the dot product of them divided by their norms. Oh, I should probably also, I didn't actually say what these things are. The norm of a vector is the dot product of it with itself. I should say the norm squared is the dot product of it with itself. And this is the magnitude of a vector. Well, okay, let me actually be a little more precise. Let's get rid of this 2 and do square root. The norm, the magnitude of a vector. Yeah, so this is maybe something we're familiar with, but just kind of a recap, because we're going to use this less as you may have seen it in calculus classes and more linear algebraically. So, any questions on what kind of the setup is dealing with? Right, and so now we come to the kind of pivotal definition, which is just the definition of perpendicular vectors. So we say U and V are orthogonal if U dot V equals 0. So this is all just a recap of the lecture. You don't want to go too much into detail, but you're welcome to stop me for questions. So here just is just another word for perpendicular. And so this is kind of the definition of perpendicular for Rn, where n is greater than 3. We say they're perpendicular. We call them orthogonal if their dot product is 0. So anytime you see a dot product being 0, you should, in your mind, imagine kind of two perpendicular vectors. So U dot V equals 0, kind of in your mind, visualize maybe some vector U. This is in Rn. And then you want V to be perpendicular to it. Yeah. So this will be pretty useful. So why is this nice? Why is this useful? Okay, so why is this useful? The reason it's useful is because when you have orthogonal vectors, it's very easy to write another vector as a linear combination of those vectors. So expanding vectors, expanding a vector as a linear combination of orthogonal vectors is easy. So let's see how that's done. Right, so because normally to do this, we need to set up a system of linear equations. Right, we need to say this vector is some linear combination of some other vectors, and we get some matrix equation. So we need to solve a linear equation. We solve a linear equation. But with orthogonal vectors, we no longer need to solve this linear equation. It's a lot easier than that. So let's see. Let's maybe do an example. Well, let's keep it arbitrary, and then we'll do a concrete example. So let's say B1 through Bn are orthogonal. Right. What this means, remember, is that i.e. we say a set is orthogonal if each pairwise vectors are orthogonal to each other. So i.e. Bi dot product with Bj equals 0 for all I not equal to j. For all pairs of vectors here, they're all perpendicular to each other. Right. So if these vectors were in Rn and we had 3 vectors, then we could do like the x, y, and z axes. In R3, B1 equals 1, 0, 0, B2 equals 0, 1, 0, B3 equals 0, 0, 1, right? For example, or you could have other things, right? Or any 3 sets of vectors that are linear, that are perpendicular, right? You could take, instead of the x, y, and z axes, you can just like rotate them all in some way, and you get still as long as they're still all perpendicular to each other. Yeah, question. What's up? Was there a question? 0 here. Yeah, so this is the number 0, by the way. Yeah, so this is yes, 1 second. Okay, hopefully that should have worked. Yeah, because dot products take in 2 vectors and output a scalar. Yeah, good question. So the question was, are all orthogonal vectors linearly independent? So that was the next thing I was about to say. So there's a proposition. Orthogonal vectors are linearly independent, which intuitively we kind of make sense. It makes sense to us. So if we have a bunch of vectors and they're all perpendicular to each other, there's just kind of no way you can get some linear combination of them that equals another one. So this kind of intuitively maybe makes sense just from the geometry of Rn. I won't prove this as proven in lecture, but yeah, anytime you have orthogonal vectors, they're automatically linearly independent. So in fact, if these are all vectors, if you have n vectors in Rn, so going back to our example, what can we conclude about the set B1 through Bn? So there are n of them. They're orthogonal. They're all orthogonal. The proposition implies that they're linearly independent, and so in fact, they also span Rn because there's n of them. So this is actually a basis for Rn. Yeah. So this collection of n orthogonal vectors actually forms a basis for Rn, whatever they are. Right, we're going to keep it a little arbitrary for now. So if we have another vector, if x is in Rn, then because B1 through Bn is our basis, then we can write x as a linear combination of B1 through Bn. Then x equals some linear combination of them. We'll do C1, B1 plus Cn, Bn for some C1 through Cn. Right? And so this is what I was saying before. So you have n orthogonal vectors, you have another vector, x, and so you want to write it as a linear combination of these vectors. And so normally to do this, ironically, normal is also another way to say orthogonal. But normally we need to solve this linear system. Right? We need to form a matrix with B1 through Bn as the columns, and C1 through Cn are the coefficients you're solving for, and x here is the vector on the other side that you're solving for. But with because B1 through Bn are orthogonal, we get an easier way. Okay, so I'm gonna erase this board. So how do we solve for these coefficients? That's the question. Let's see. I'm gonna just write that again here. X equals C1 B1 plus I'll do C2 B2 plus Cn Bn. Right. So what happens if we were to take X and we were to dot product with, say, B1? We can do that. We can just take a vector and dot product with another vector. Then we get C1 B1 plus C2 B2 plus Cn Bn dot product of B1. And then a nice thing happens, right? Each one of you get a bunch of zeros, right? This dot product with B1 is 0 because B2 and B1 are orthogonal, and Bn dot product with B1 is 0, and all of these intermediate ones you get as 0, and the only thing that survives is this first term, right? So you get C1 B1 dot B1 plus a bunch of zeros. So this is one of the nice properties of dot product. They distribute. Dot product distributes over sums. Right, but this is great because now C1, we can just solve for it. This thing on the left-hand side, this is a number. This is a real number. This is a real number. So we can just solve for it. Right? You just automatically get the real number just in this formula. Right? You don't need to solve any linear system because they're orthogonal. You get the coefficient. And so this is just, maybe this is a theorem or something at some point, or a proposition. If B1 through Bn are orthogonal, these are all in Rn, x in Rn, then x equals, so some linear combination of B1 through Bn, and the coefficients are just given by an exact formula, x dot B1 over B1 dot B1, and x dot Bn over Bn dot Bn. And so you don't need to solve a linear system. And that's why it's nice to have orthogonal vectors. Any questions so far? Okay. Maybe we can do an actual example with some numbers. So let's define B1. Okay, now I need to come up with 3 orthogonal vectors. And some other vector. And the question will be, write X as a linear combination of B1, B2, and B3. Okay. 1, -1, 0. 1, -1, 2. And does that work? No, that doesn't work. Let me just pick an example from the book so I don't have to make one up. Okay, here we go. Three, one, one. Oops. -1, 2, 1. And -1, -4, 7. Okay, hopefully that's orthogonal. And then let's do X is just, I don't know, 0, 1, 2. Hopefully those numbers are not awful. Okay, so this is just an exercise for everyone. Shouldn't take you too long. Just practice computing some dot products. And then after this, we'll talk about orthogonal complements and orthogonal projections. So I'll give everyone maybe a minute to work on this. In the meantime, you can ask me any questions. I think this is from a previous one, so I'm going to lower that unless there's a question. Okay, let's go over this briefly. So all you need to do is compute the coefficients, and we already have a formula for that. So you just want X equals C1, B1 plus C2, B2 plus C3, B3. And we have a formula for each of these coefficients. C1 should be X dot B1 over B1 dot B1. C2 should be X dot B2 over B2 dot B2, and so forth for C3. And so you just compute each one of these. I don't know what you actually get, but you should get a number for each of these. And then if you want to check, there's an easy way to check. Once you find all these coefficients, you just add them all up and you should get X. So that's just a nice way to check. I guess also technically, we should check B1, B2, and B3 are actually orthogonal. I said they were, but you should probably check they're orthogonal. Right? Because if they're not orthogonal, then this doesn't work. Right? This is only true if B1, B2, and B3 are orthogonal. So you really need that to be true. Okay, let's talk about, let's do orthogonal projections first. Let's talk about this. This is pretty important. Is there a question? Sorry.
So when you check if three vectors or like three or more vectors are orthogonal,
Mm-hmm.
like if you just check if like do you need to check like that they're orthogonal with like each other like individually? Like for example,
Mm-hmm.
with three vectors, you check if the first one is perpendicular to second, then first to third, then second to third, or can you just assume that if like two vectors are like orthogonal to one of the vectors, then like those two are also orthogonal to each other?
Yeah, good question. So you need to check every single pair. So you need to check B1 is orthogonal to B2, B1 is orthogonal to B3, and also B2 is orthogonal to B3. Because it's not true that if you have two vectors like B1 and B2 and they're orthogonal, and you take a third vector, B3, and you just check its dot product with B1 and you get 0, it doesn't imply that its dot product with B2 is 0. So you need to check all
Okay,
pairs.
thank you.
Yeah, because you could have something like this, B1, B2, and B3. Right, so B1 and B2 are orthogonal, B3 and B2 are orthogonal, but B1 and B2 are not orthogonal. So you need to check every pair. Okay, let's talk about orthogonal projections. I'm going to erase this board. Orthogonal projections are extremely important. So they're kind of the, I mean, there really are the foundation of like a lot of techniques that are used just in various machine learning and data science methods. So anytime you have some high dimensional data, that's hard to deal with in a computer, it's just too big, you can project it to a lower dimensional space using orthogonal projections. And so this is very useful in applications. We're going to talk a little about it in the class later, e.g. Linear regression. But also something like PCA, which we won't talk about, but very useful in various machine learning techniques. So what is an orthogonal projection? So the classic picture I'm going to draw for the next month is you have some subspace, W. This is in Rn, say, so this is some big subspace. It's not necessarily two-dimensional. And you have some vector coming out of the subspace. Right? And you want to find the closest vector, closest in W to V. Right? So you want to kind of pretend V was in W and see what its shadow would be in W. And the way you do that is you imagine looking from above. You imagine there's the sun here, kind of perpendicular to W. There's like a sun. And its shadow it casts is going to be this vector. Yep. So this is the orthogonal projection of W, of V onto W. And it's defined to be the vector. So we call this we call this, say, v hat. It's defined so that if you take the difference between v and v hat, you get this orange vector. This orange vector is v minus v hat. This is like 0 over here. It's defined so that v minus v hat needs to be perpendicular to w. And then we kind of unwrap that and we can figure out what v hat needs to be. So let's actually do that. Let's do a small example. And then we'll do a two-dimensional. Let's do a small example is where W is one-dimensional. And then we'll do a bigger example where W is two-dimensional. And then we'll see the patterns. Let me pick one. Okay, let's compute the orthogonal projection of 1, 7 onto the line the span of the vector -1, 3. Okay. So now I'm going to erase this so I can draw a smaller picture. So now W is a single line. So I'm going to redraw this as a line. It's a -1. I'll try to draw it to scale too. So let me draw my normal coordinate axes. So W is the line. I think I can actually draw. Okay, great. This is W. And then we have a vector V. This is V. And we want to compute the orthogonal projection. So we imagine projecting it down. Imagine there's kind of a sun over here, and we want the shadow. And the orthogonal projection is going to be this vector. So the orthogonal projection should always live inside your space W. This is W. Let's call this something, V hat. So how do we solve for this? Well, we want the difference between them, V minus V hat, needs to be orthogonal to W. So we can just solve for that, right? Here's V. We don't know what V hat is, but we can just put in some random numbers like A and B or something. We can take their difference and dot product and set that equal to 0 and then solve for A and B. So we can do 1, 7 minus V hat. This is, let's say A, B equals V hat. the dot product of this with negative 1, 3, that's equals 0. And so you can just, you get an equation, you can solve for A and B. Right. So I'll do this another way using maybe some more matrices, or, well, no, we can just figure that. So we get 1, 7 dot, I'll still do this, negative 1, 3. I'll put this V on the other side, equals AB dot negative 1, 3. And so you just get A is 1, or so you can take the dot product of this, and you get negative 1 plus 10 is 9, and you get
wouldn't it be 21?
Hmm?
Wouldn't it be 21 instead of 10?
Oh, yeah. Sorry. Uh, 21 minus 1 is 20. Right, and then you can just scale it however you want, because you know, we just get like any scalar multiple, so you can just pick a scalar multiple you want. Let me give you a better way kind of to do this, so you don't have to keep doing this like in an ad hoc way every time. Because there's a formula for every time we want to do the projection that we're just going to basically use each time. And it's the same formula we had before, right? So V hat, we want it to be a linear combination of, so we should pick a basis for W is so this is maybe a better way because it'll generalize to bigger spaces. V is a linear combination of basis vectors, sorry, orthogonal basis vectors. That's the important part. So let's pick a basis, pick an orthogonal basis. Fortunately, W is just a single line, so we can just pick a single vector. B1 is negative 1, 3. And then the theorem is that V hat is the same formula we had before for V, for writing V as a linear combination of B1. So in general, you might have some more things, but in this case, we just don't. We only have one basis vector. So for us, we can just plug this in. So let me do that over here. So V hat equals V was 1, 7 dot B1 is negative 1, 3 over negative 1, 3. And so you're going to solve for this. We just did this 20 over 1 plus 9 is 10. So you get negative 2, 3, 6. And if you plug in negative 2, 6 here, you get, you'll see it's the same. So this is maybe a better way, because here you need to like pick the right scalar. So While this like method over here, you can like reason through what v hat needs to be. This theorem will help you because it'll give you a general way to find orthogonal projections. That's supposed to be a star. So let's do a harder example where W is two-dimensional. So let's do another example. W is going to be a two-dimensional space. The span of, let's say, 1, 1, and negative 1, 1. 1, 1, 0, negative. So these are in R3. Let V equal 2, 7, negative 3. And you want to find the orthogonal projection of V onto W. So why don't everyone try to work on this for a little bit? We'll do this for like 2 minutes or so, and then I'll go over it, and then we'll end there probably. While you're working on this, you're free to ask me any questions. And in the meantime, I'm going to draw a picture as best as I can.
So is there a reason why the formula for the orthogonal projection is the same as like the linear combination formula?
Yeah, I guess we should go to the proof of that. One second. Okay, I'm gonna start over this. Yeah, so I mean, one way is just to write down the formula for V hat and just check that it works, right? You should check that that the difference between V and V hat is, so you can just check that V minus V hat is perpendicular, is orthogonal to W, which means that you should check that V minus V hat is this sum of coefficients. And you want to check that this is orthogonal to W, so you want to check that its dot product with each BI is 0. And that's just, you just distribute and you see that it is. So you get V dot BI minus, the only thing that survives here is this BI term. And you get V dot BI. And this equals 0. So, I mean, that's kind of why this is the formula, just because it's exactly what it needs to be so that the difference is orthogonal. Right? This is like the defining property. So V hat's exactly what it needs to be so that this difference is orthogonal to W.
Okay, that makes sense.
Mm-hmm. So I guess you could keep these coefficients, if you wanted to figure out these coefficients, you could just keep them all arbitrary and then solve for them. And you'd get Ci equals this. Kind of the same way. Okay, let's do this example. Because it'll give you a picture of what orthogonal projections are. So let's draw W. And these are all in R3. So I'm going to attempt to draw a picture in R3 on my tablet, which is, so this is the x-axis, this is the y-axis, and the z-axis is coming out. You have to maybe squint for your perception, or perspective, I mean. Okay, here's z, here's y, here's x. Okay, W is a span of 1, 1, and negative 1, 1. So first of all, are they orthogonal? Those two vectors? Yeah. Just the dot product is 0. And negative 1, 1. These are orthogonal. Okay, and then we have V. So W, this is really the xy plane. You know, just pick two vectors that are orthogonal. And then V over here is 2, 7, negative 3. I wish I had chosen a positive thing. Okay, whatever. You know, I'm just going to change this to positive 3 so I can draw it. So V is somewhere over here. The answer doesn't change, except it changes from negative 3 to positive 3 or something. Or actually, the answer doesn't change at all. So W is this whole xy plane. Right, and the orthogonal projection is like, you look from the z-axis and it should be just dropping down V onto the xy plane. So just intuitively, you should get V hat just equals, you should just forget the z component. Right, and let's just check that that's true. Let's check V hat equals, so we should take V dot 1, 1, 0. We can just do this in our head, or 1, 1, 0 over 1, 1, 0 dot 1, 1, 0 times 1, 1, 0 plus 1, 1, 0. Okay, I just did that one in my head. And so you get 9 halves 1, 1, 0 plus 5 halves negative 1, 1, 0. And so you get 2 and then 7, 0, exactly V hat. Yeah, so it matches our intuition. And let's do one more example where, what if we were to change, so this is W, and we gave two basis vectors. Here's B1 and B2. What if we were to change B1 and B2? So that instead of these two vectors, what if we chose a different two sets of vectors in W that are still orthogonal? So what if we change them, let's say, to 1, 0, 0, just the x and y axes, and 0, 1, 0. Right, so now we have a different orthogonal basis of W. The question is, does V hat change? And intuitively, it should be no, right? Because V hat is really just the orthogonal projection, right? We're still just looking as if the sun was on the z-axis, and we're kind of looking down. Right, and that doesn't change if we change B1 and B2, right? W is still the same space. We just chose a different basis. And so, in fact, the orthogonal projection should be the same. And if we were to calculate it, we get exactly the same thing. We take v dot 1, 0, 0. If we were to use these different basis vectors, times 1, 0, 0, plus and we get exactly 2, 7, 0. Right? And so the moral that I want to leave you with is that the orthogonal projection doesn't depend on the basis you choose. So that's the key. That's the takeaway. Orthogonal projection does not depend on the choice of orthogonal basis chosen for W. Right? But you still need to choose an orthogonal basis. Right? If I chose a non-orthogonal basis, then I did this thing, it wouldn't work. Right? So you still, whatever basis you choose needs to be orthogonal, but it doesn't matter what basis you choose as long as it's orthogonal. That the orthogonal projection V hat will always be the same because it's still just, the subspace is kind of independent of what coordinates you put on it. Okay, so I think I'll end there. There's a bunch of true-false questions on the worksheet to test conceptual aspects of orthogonal projections, and we'll do a lot more of this after spring break. We'll talk about orthogonal projections. We're going to then talk about, this is just a foreshadow, we're going to talk about how to find the best fit line for a bunch of data points. We're going to talk about, to get best fit line, so linear regression, and then we're going to talk about how to find orthogonal bases, because they're not always easy to find, and it's just some more theory after that. So I'll leave everyone with that, and I'll be on for maybe until 11:10 for more questions if people have.
Thank you.
Thank you.
Hmm?
Thank you.
Thank you.
Thank you.